We are going to talk about semiconductors. So we are going to look at briefly into different concepts of semiconductors. So I will have a series of short videos today, but different concepts which are there and will be helpful in basically when you are understanding any semiconductor devices, right? So that is the basis of understanding the devices or MOSFETs, whatever we were talking about. Okay. So let's start with our famous MOSFET, which we were working and we talked about in one of the video of the structure of this symbol also. We saw that it has three terminals, the gate, which physically was a metal and oxide, which was on lying on a piece of semiconductor, which is silicon, right? So this is our semiconductor. And then we had other pieces of source and drain metal to apply the electric field so that our current starts to flow in this region, right? That is what the main operation of the MOSFET which we saw. So now the question comes, what is a semiconductor? What is this? So you are saying there is a charge coming in. What is this charge? Where it is even coming in the semiconductor? How do I really imagine that what is this semiconductor? So semiconductor, so you see that widely we divide the three classes of materials. You say some are metals, which all you see in this. These are your dielectrics, oxide, or what we say as a very big is the insulators. Then you have your semiconductors, right? So these are the three widely uh, classification or widely used classification of the materials which we do. Now the question is, if you are given, let's say, a material which or a piece of some rock which could be a semiconductor, which could be a metal, but how would you distinguish that what is a semiconductor and what is a metal, right? So you would say, okay, if you give me a piece of rock and it could be a metal or it could be a semiconductor, what would I do? You say, okay, I am going to apply, let's say, I am going to put some electrodes into this and the other electrodes onto this. And assuming that the electrodes which I have put in are not really resulting in a very high resistance, assuming that in this rock, and I apply a supply, right, and I'm recording the current, what is going across this. This is a small experiment which you can do, right, and see how is the resistance. So what you would plot, you will say, okay, this is the current which is going through this metal. How is the resistance of this thing is vary. So if it is a linear, which is what Ohm did, right? Ohm did an experiment with the conductors with different thicknesses and everything. He plotted this I and then he concluded that V by I, there is a ratio which is fixed for a conductor or whatever he was using. And he saw it was basically the resistance of that conductor. So this is what we know as the Ohm's law or the experiment which he did, right? Now, what we are saying is, let's say you are given, so this is, if it was a metal, you would likely see this kind of characteristic, which is what Ohm did, right? But suppose if you are not seeing this, right, and you are seeing very low current, would you be able to comment that that is semiconductor? Because that could be an insulator also, right? Very low current. So then how do you really check? Because this thing, if you don't see any current or very small current, right, you could say this is could be, can it be a semiconductor or it could be an insulator? How do I conclude that what it is? So then comes a very important variable other than the electric field which you are applying, which is called temperature. So temperature is one of the key thing, a key variable, input variable, which can help you distinguish what is a semiconductor and what is an insulator, right? So how does it do that? Because you see, when you increase the temperature, let's say So this was done, let's say, at certain temperature, right? For example, let's say you had this experiment done at room temperature, for example, 25 degrees C. Now you increase the temperature and probably you started seeing some current, right? Let's say some current like this. Let's say you heated it up to 100 degrees C. Now, what is this happening? What is the property? Oh, with the temperature, my current is increasing. That means I do see some current. So that is a very, very important property of what semiconductor consists of, right? So what it does is, so if you understand semiconductor, semiconductor is basically like, so all this conduction which we see is happening by electron, right? That is no problem in understanding that this is the electron is the cause of current, right? Whichever we are talking about in this. So now in the semiconductor, what is that you are going to see that you typically can understand semiconductor as that there are a band, or let's say a p, somewhere there are rooms which are filled rooms, right? So these are the rooms on this floor which are filled. Filled means, okay, and who is occupying these rooms are electrons, okay. So at this floor, which is what we know as the valence floor or valence band, so in this floor all the rooms, right, so all the rooms are filled. Then you see another floor which is obviously after certain height, right? And this is another floor. So let's say this is floor 1, which you see, right? This is floor 0 here. So this is just our naming of the floors. This floor is what we know as the conduction band, right? Conduction band. So now electrons is occupying these floors, which is floor 0, right, for us. And floor 1, we see, oh, there is no electron. Why is that so? There is no electron. Who decides that there is no electron there? So that is what is a very important property which we know as the Fermi energy, right, or Fermi level, which we know as. So what is a Fermi level? Is similar to a, let's say, a level in a bucket when you have, or level which you are having in a hotel, right, which tells you, let's say, when you are seeing that, okay, these rooms are vacant, these are empty, kind of, this is a level which indicates that which rooms are empty, which are most likely filled. So Fermi level indicator of how many rooms are filled on floor 1. Floor 1 is your conduction band. Okay. So that is the indicator which this Fermi level is. So let's review the terminology again. So the floor 0, where you will always see the rooms filled, right? That is your energy, your valence band. That is what we are calling the name valence band, VB, which is your floor 0. There, then you have a gap between the two floors, and after the gap you find floor 1, where we may or may not see electrons, right? And who decides that is what we are saying. There is an indicator, which is what we know as the Fermi level, which tells us how many rooms are filled on floor 1, right? That is what the idea is. Now, what is a semiconductor? So this semiconductor means that this is, or the gap between the floor is also what we know as the EG, or we know as the band gap, which is the spacing between the floors, right? So obviously, you know, with between the floors, when you have a gap, there is no room there, right? There's no room. It's basically a gap, which is what we know as the band gap, that there are no rooms there. The electron can occupy any state or any room, right? So then now what happens when we are increasing temperature? So what happens? So this is, let's say, the starting point of the semiconductor where all the electrons are filled in the floor zero. And what you started doing, you started ramping the temperature. So when you started ramping the temperature, what started to happen, that these electrons, because now they have energy in the sense that suppose somebody gives you, you have seen probably a trampoline, right? So on a trampoline, if you give, somebody gives you energy to push back, then you are able to likely jump, right? Because you will gain the potential energy to jump. And that is what exactly happens with the electron, that it is like a trampoline. So once you give a temperature to it, it gives, or it gets that energy, and it has a probability that it can jump to the top floor or the floor one, right? And that is what again would be indicated by EF, because that would move up and down depending on that how many rooms are filled or empty, right? So then we see that this is what is happening with temperature. When we are increasing the temperature, more and more electrons are going to jump to the floor one. Okay, and that is the basic property of how in the material, if you have studied basic chemistry also, you would have studied that when you have energy, the electrons will like to, because they get that potential energy, and they may go to higher floors, right? And it is very likely that they may come down also, right? So that process can also be happening. But what we see is that if we are constantly keeping the temperature high, these electrons will be going to the higher floor, right? And what, as a result of this, you can say at floor one, I have more electrons, or the electrons at floor one, the concentration of electrons increases with temperature, right? Increases significantly with temperature. And that is one of the key property which you see in semiconductor, that we see that if temperature is absolute 0 Kelvin, right, there is no energy in the system. You will see there is no free electron which you are going to see. So yeah, these electrons which come to, or they are reach to this floor one, we say they are relatively more free than the people who were bound at the floor zero, right? That is very likely, because if you go up and up, you likely you are going up for more freedom. And that is what these electrons are also feeling. So they are more free, in a sense that there are lesser number of these than the what is there on the floor zero, right? So then we see that these, what we terminology typically use is we call them free, but they are relatively free because they are still in the material. They are not free that they came out of the material, right? So they are still in the material. So what we see is that these free electrons, right, which we know as N, some terminology, N is the density of electron or electron density. You see, it's very close to zero, right? Because at 0 Kelvin, there is nothing, no energy in the system. And that is why the semiconductor would behave like a insulator. And that is the reason why we were seeing that for some temperatures, the semiconductor was not even showing any conductivity, and it was feeling like that it is like an insulator. But what happened when we increase the temperature to much higher temperature, like here we were going to 100 degrees C, we started seeing that N started increasing significantly, right? And that tells us that there is a transition which has happened in the semiconductor, that it has turned into metallic like. That means now it has lot of charge, which is there. Charge in the sense, lot of electrons which are there, which defines that it is behaving like a metal. That means there is now charge to flow, right? So that is what you see. The basic property of the semiconductor is that the temperature, if you want to distinguish a semiconductor from metal and insulator, temperature is one of the important variable by which you can look at how is the property of this material changing. Okay. So in the next video, now we are going to see a very important concept which we use typically to define transport. So that can help you understand the equations also of the semiconductor or the transport in the semiconductor, which is called electron and hole.